Okay, so ladies and gentlemen, okay. Maybe I'll stop that. Okay, boom. Delete and yes, delete. Boom. Okay, so this will be CCM in practice. In practice. Okay. Okay. Okay, so ladies and gentlemen, for those joining us for this lecture, welcome and apologies for being here behind schedule. We've just finished discussing a very basic characterization of CCM based on the successive concepts associated with state spaces, with the notion of coupled nonlinear systems, the fact that information from one part of them can, in fact, tell us about the other parts of the system. We, moreover, talked about the notion of embedding, and particularly delay embedding, this process by which, extraordinarily, and taking advantage of Flores-Taken's embedding theorem, given empirical data about one piece of a complex system, we could use that information to reconstruct the underlying structure of state space for all the elements of the system that drive the one on which we have data. So just as, for example, knowing about the fact that the number of hairs within a predator-prey model is dropping very rapidly tells us there must be a lot of predators around. We can often go from data about just one piece of the system, here hairs, to gain an understanding of what's going on, what must be going on elsewhere in the system. Here, the fact that there's a lot of predators, or the fact that that we're getting lots of infections going on right now tells us there must be a lot of susceptibles as well. So within that lecture, we discussed the basic procedures associated with CCM. The convergent cross-mapping technique, first introduced as a brilliant contribution by Sugihara and colleagues to assess the existence and the strength of a connection between, of causal connection between two variables, each of which you have a equally spaced sampled time series. So if we have a time series for y and we have a time series for x, using this contribution from Sugihara, we can assess the degree to which y is driving x over time. Okay. In order to do that, in order to assess that the existence and the possible strength of a causal connection, we perform a cross-mapping, as it said, from x to y. In order to do this, we create a shadow manifold for x. We take the information on x and use it to, using this embedding procedure, to reconstruct the state space of the broader system that's driving x. And we do so for different library lengths L. And we examine how the correlation between the value of y at a particular point and the value of y inferred from nearby points to that index point. So if we have an index point at time t, and secretly has a value y of t, we look to the degree within the reconstructed space, the shadow manifold M sub x, reconstructed only from x. We look to the degree to which the estimate for the value of y of t, value of y at t, can be accurately estimated from the value of y at nearby points to that index point in the state space reconstructed from x. Okay, and we see how the correlation between the true value of y and the value of y inferred from nearby points within this reconstructed state space M sub x rises as L rises, as this library length rises. So this is all characterized in the previous talk. And what we've seen is that we get rather different pictures when we have a causal connection from when we have no connection at all, when we have merely a statistical dependence, when x is correlated with y. And with a causal connection, if y is impacting x, means this correlation between the actual value of y versus the inferred value of y based on nearby points within shadow manifold x, the correlation between those two goes to 1 with large enough L's. If there's no noise to interfere with it. And the stronger the causal connection and the less the noise, the faster the convergence will be. And the key factor to look for here is not the strength of that correlation alone, that rho, but rather how does it change as L rises, and to what does it converge? We saw that if there's a correlation between x and y that's not causal, we can still get a rho that's distinctly non-zero. We saw some examples of that in the last talk. But it won't, the value of rho won't be going up on an ongoing basis as L rises. And it will in fact often converge from upper and lower sides in a kind of envelope sort of way that we'll be seeing later in this talk as well. It bears note that we can get fairly significant values of rho due to correlation between variables, although I rarely see them myself above something on the order of 0.5 or so. But these should not exhibit strong convergence with L. Okay. So within this talk, I want to speak with you about some practical techniques for improving the ways in which we assess causality using CCM and convey some realizations from thousands of hours of experiments performed with CCM on ground truth examples where I know the true situation and I'm assessing findings using CCM. And I'm going to try to convey these realizations in a structured way, starting with kind of a greatest hits of realizations, and then going systematically and looking at the effects of various factors that are of significance: effective value of tau, effective value of E, the impact of noise within the system on your results, etc. But I want to convey practical guidance here, and this will require stressing a few points which are of great great significance when pursuing this sort of work, not merely conceptual structures. Okay, so one point is that it is absolutely essential and fortunately well supported by the library contributed to REDM by Sugihara and colleagues to perform many realizations for a given window of length L. So when we are growing L over time, we're not merely taking the first L parts of a time series. We are taking different element or different windows of length L from different points within that time series to assess the value of rho with respect to each of them. Okay, and it's absolutely essential that we do that so that we can get a sense of the variability in L, number one, and number two, that we're not thrown off by temporal effects, where if we only do it for the first part of that time series, say for each L equal 10, L equal 11, L equal to 12, we're only looking at the first 10, 11, 12 elements, rather than later windows of length 10 or 11 or 12, will often be thrown off by temporal sequences. More to the point, we will further be thrown off by just the variability for different subsets of the data in the rows that obtain. So commonly, we use 500 to 1,000 as the value of L. Sometimes I'll go as little as 250. But I worry about the about flukes if I go with L below 250. That just we'll see values coming out for the correlation that are not representative of the broader sample. So I try to always do it 250 or more myself. Secondly, the choice of tau can have a big impact on results, and tau equals 1 is not always the best, does not always yield the best results. And I would encourage scanning by the value of tau at first to get a sense of if tau equals 1 will be sufficient, or if you need tau that is larger. This is the delay embedding. And those of you who have watched my previous presentation will recognize that this has a very big impact if you are sampling sparsely within the space. And even if you're, excuse me, sparsely in time. You're not sampling at a very high frequency rate. If you have very large tau, it can actually lead to pronounced changes in the perceived geometry of the space. But if you are sampling very, very frequently, you will want to use larger values of tau in order to avoid, to lessen the effects of autocorrelation and to essentially get the embedded space, the trajectories in the embedded space off of the diagonal region. Okay. A third realization is that CCM does pick up both direct and indirect correlation. It's not a matter of merely direct correlation, it also picks up indirect. So if X impacts Y and Y impacts Z in the underlying system, and you ask via CCM about whether there's a causal impact of X on Z, the answer will be generally yes, that there is, because there is some causal chain, some causal pathway by which X influences Z. In a way, this is reassuring. It's not going to say no if there is an impact causally, but it's just not direct. But it's something you want to understand, because if you come away with the understanding that X impacts Z, but actually it's purely through Y, you can't dismiss Y. Don't think it means that X impacts Z necessarily directly. It may be indirectly. There may be mediating variables there. Other elements of that causal pathway that you need to consider. Data conditioning, ladies and gentlemen, can make a really big impact on perception of convergence. First order differencing in the data can at some point, it can in some cases be very important. And I like to engage for many of my cases in standardization. What I mean by standardization is the classic statistical standardization where we'll take a time series and we will transform that time series so it has a zero mean and a unit variance and standard deviation. I don't do that as often as I do first order differencing, but it may be a useful technique to undergo. Now, it is, in my experience, it is absolutely essential to examine per realization density plots for your system. By per realization plots, I mean plots like this, which plot out for a given L a density plot of the rows encountered. Okay, so you remember before I argued that for a given L, we want to sample many different windows of length L, 500 to 1,000. So for say for an L equals 750, we might sample 750 times, 750, excuse me, 1,000 times, say, windows of length 750. And for each of those windows, measure a row. And here we have plotted out in a density plot the value of those rows as generated by those successive realizations, each with L being 750. So we might have 1,000 realizations. Some of them yield rows down here. Some of them yield rows up here. But most yield rows in this high probability density region here. I find those plots absolutely essential. And we do have a library that runs on top of our EDM to produce them. I also find it useful to examine high-level surveillance using mean plots, particularly for tau. Okay, and that gives me a sense of sort of where to concentrate my energies. If I see big differences in the behavior for different tau, in particular rows that are much larger with larger values of tau, I'd consider very seriously using those values of tau or investigating their impact. Okay, more realizations. Changing E in the presence of noise, and particularly high noise, can change the shape of the curve in pronounced ways. Okay, E here, ladies and gentlemen, is the embedding dimension. So remember in that earlier talk, I noted how in delay embedding, for each point within a time series, putting aside boundary effects for simplicity, for each point in a time series, each index in a time series, we create a vector. And we place that vector into a space, which we call the shadow manifold, as constructed from that time series. That vector is of length E. I'm just using E to describe the point of the vector. And we have to choose an E. That isn't given to us by heaven. We have to choose an E. We have to somehow come up with an E in which to embed it, just as we have to choose a tau. Those are two key parameters for CCM that are not handed to us. And Sugihara et al., as part of their extraordinary contribution, have suggested ways of picking an E, such as through the simplex method. But in my experience, it's worth doing some experimentation. And the point is, in the context of noise, when we have a noisy system, which we typically do for a wide variety of real-world systems, where there's measurement noise, where there's noise in terms of the processes, the underlying processes, essentially stochastics, it turns out that changes in E can change a given connection from apparently being causal to apparently being non-causal, okay, or vice versa. And we'll see some examples of that. So you want to choose your E judiciously. CCM is best suited for assessing causality between variables that are predominantly autonomous. By that I mean they're not directly functionally dictated one to the other. For example, suppose we had a time series of x of t over t, and then we have another time series y that's simply a square of the values of x, of the corresponding values in x of t. That would not be very interesting to perform CCM on. It turns out that in both cases, the one would totally determine the other. And Tsukihara refers to this in their science paper as one is so forcing the other that that they're not really independent of one another, and one will appear to totally cross-map the other. And we're interested instead dealing here, the best applications of CCM that I've found are to coupled nonlinear systems where you have some degree of autonomous character to the different pieces. And in the earlier talk, we characterized some systems like that, right, where we have predators and prey, or systems where we have people, mosquitoes and birds, for example, or we have susceptible, infected, recovered individuals, etc. Here, here we are dealing with a situation where there's coupling, but it's not. It's one variable is not simply a function of the other variables, or even the other variables plus some noise. Okay, some more. So I have done some work with the mean arithmetic error as an alternative to rho, but I find that it's not as helpful as using rho. Sugihara et al. Introduce mean arithmetic error within some of their supplemental material, as I recall it. I haven't found it as helpful as their basic method with rho, although it's possible that I'm simply not working with examples where it would be useful. The presence of a large amount of noise within the systems that we're characterizing, systems which give rise to the data generating processes, as we call them, can lead to misleading conclusions regarding convergence, ladies and gentlemen. It can, in some cases, obscure genuine convergence, particularly with weaker causal connections. We saw some of that in the last talk. The bigger danger here is it can interact with E. And if you choose an E in a way that's not that judicious, you can end up coming to misleading conclusions. Okay, when you're dealing with empirical data, if you look at means from CCM, they can be ambiguous. And in my view, it's absolutely essential, as I noted on the first realizations, to have per realization plots. If I couldn't get per realization plots, I would be very hesitant to use CCM on a regular basis, because I think without the added insights from these plots, I think it'll be very easy to come to mistaken impressions. It's highly advised to make use of these plots to determine, to distinguish causal and non-causal cases for some of those envelopes we saw last time, and we'll see a lot of later in this presentation. So these are some key realizations that have come hard-won from hundreds of examples that I've run with this now, most of them with ground truth to directly refer to. I know the truth situation, and I'm rigorously assessing the viability of these methods and different variants of these methods with different metrics like mean arithmetic error and rho, with different values of E, with different values of tau, with different schemes as far as first differencing or standardization, etc. Having made these sort of overall realizations, these syntheses of my findings that I think are absolutely essential, sort of desert island CCM knowledge. If you're going to apply CCM, you need to know about these things. I'd like now to talk about particular subsets of these and to expand on a few, okay? There's going to be lots of graphs coming up, and as always, I'm glad to share these, okay? The first concerns the effect of embedding dimension E. Okay, what is the effect of E? When I first started getting started with CCM, I had a real fear that if I choose the wrong E, I may come up with terribly misleading results. I didn't know how essential is it for me to get, to just nail the E. How can I find that best E? Since that point, my worries have allayed a fair bit, and you'll see why. But it is still really important to pay attention to E. Okay. Oh, out here, this side. I can plug it in. Yeah. So we're going to talk for the next few minutes about the impact of E. So, ladies and gentlemen, if we have an E that's, and I'm actually not sure from my experimentation whether it's a matter of it being high or whether it's simply a matter of it being far off. But E can lead to slower convergence. It can slow down the rate of convergence as rho goes up with the length of L. The effects seem, if you're not dealing with noise, if you're not dealing with a situation where there's pronounced noise, the effects of E are actually quite a bit smaller than you might think. Actually, CCM is highly robust to different assumptions about E if there's not much noise. It's kind of amazing in my view. Even if you have E half of the value that it should be by the intrinsic dimensionality, it actually can work very well. But the real kicker with E is that it interacts with noise. And in the presence of noise, if you have high or far off E, and to be honest, I'm not certain which it is. I think it's high E in this case, will lead to spurious things that may appear causal but are not. Okay. In some cases, it can also be such that you can get things that are causal that with noise get washed out. Okay. Often there's a pronounced disparity between the values of rho that can come about by changes in E, and the disparity between values of E seems to be the result of noise. Okay. And you don't, so Sugihara in his science paper, I think, or one of the other papers, an absolutely brilliant contributions, makes a comment that I haven't found useful, commenting that they suggest taking the E that leads to the highest rho. I have not found that rule of thumb helpful in my work. I've typically chosen values of E based on other criteria, including use of the simplex algorithm that he suggests, but also scanning for different values of E based on mean values, and finding one that's kind of moderately high but not the highest. One of the problems with this, from my experiences, it may be that he didn't mean considering a wide range of E. If you take an E that's very, very high, like 20, 30, 40, you may get a very high value of rho, but I'd be very hesitant to consider that. So let's take a look at the face of CCM as we vary E, okay? This is for a situation with no noise, and we'll go to a situation with noise in a little bit. We'll actually revisit some of this when we talk about noise as the focus. Right here, the focus is really about E. Later, we'll talk about noise. So this is a situation for different E with no noise. What we see here on rows is a given connection from the same underlying system, the same data, analyzed with different E's. So the same underlying time series with reconstructing the shadow manifold as embedded in an E-dimensional space where E is successive columns 2, 4, 8, 16, and 32. So this differs by a factor of 16 over 1 order of magnitude, okay, between E2 and E32. And a given rho is a given causal connection. Some of these causal connections, a given pair of variables. I should not say causal connection. Some of these are causal, some are not. Some are directly causal, some are indirectly causal, some are not causal. In fact, these are labeled along here. The top one is indirectly causal. The second one down is not causal. Third is indirectly causal. Fourth is not causal. The fifth is causal, and the sixth is causal. So the bottom two are causal. The one above that, in other words, is not causal. And then we have an indirect and a not causal, and at the top, an indirectly causal. And what you'll see is for different values of E, the results here look remarkably similar. I find it utterly striking. I mean, you could almost pick one of these up and substitute for the others, and you wouldn't be able to tell the difference. These bottom two, the beaming face of causation comes through strikingly. Its friendly mean is dramatic. Even here the cases with indirect causation, the top row and the third row, these you see very clear evidence of a causal effect. And meanwhile, for the non-causal effects, they're quite similar across different values of E. Okay? Yes. Sorry. The asymptotes. Good question. Excellent question. So I would have to go look at that. We will see soon enough that they can be different, but I believe here they're essentially the same, the asymptotes. In other words, if we looked at where these, the value of rho at this point, say the high posterior density regions here, I believe they're more or less similar across these different values here. If they had noise, we would see a totally different situation. This is because there's no noise. Okay, with noise, we'll see. In fact, we'll go to that. But otherwise, these look, I think, in terms of their asymptotes, they're essentially the same, and in terms of their let's see if I could zoom in. Yeah, alas. So in terms of the shape, in terms of the asymptotes, these are basically the same. Here is with noise, ladies and gentlemen. And with noise, we see actually a very different situation. This is actually a high degree of noise. Once again, we have scenarios down here. They're actually, I think it's the same scenarios, yes. And then, again, a factor of 16 in the value of E here. But what we'll see is very different asymptotes here. And we'll see actually quite some differences in shape, reflecting the high degree of noise, okay? I draw your attention to a few features. This one here, this is a non-causal connection. This one may shock some of you, okay? If you look here, what does this look like to you? Does this look causal or non-causal? This first one. What does this look like? Non-causal. The fringe gives it away, right? How about this one? Looks causal, ladies and gentlemen, to me. How about this one here? Indirect causal. Doesn't look causal here. Looks kind of causal here. This is not causal at all as well. Definitely not causal here. This is the correct, by the way, this is the true, E4 is the true one. I showed it here. E4 will be the most appropriate here. But you notice half of this, it's actually not so distant from E4 here. But notice as you go on, this not causal starts to look pretty causal by E32. Now, mind you, this is a difference of 8 from the value we really should have had. So it's not a small difference. And if you go to, for example, from 4 to 8, a factor of 2, ladies and gentlemen, a factor of 2, you still get pretty consistent results. not causal, not causal. This doesn't look to me causal. It's high noise, weak connection. It's not obvious it's causal. But these lower ones definitely still look causal. The last two rows definitely look causal from E4 to E8. And those last two rows even look quite closely causal for E32. Just they converge more slowly for high E. But some of these others, particularly going from not causal to causal, it's scary, but it's not from E4 to E8. It's more like E4 to E32. So in my experience, you have to be quite far off with E, like over a factor of like a factor of 4 off or something to start seeing big effects. It's not a matter of within a factor of 2. I'm generally hesitant to try an E above 10, I'll tell you. I'm somewhat hesitant to do that because of the effects of what I see as perhaps the effects of high E on interacting with perceived convergence in the presence of strong noise. Sugihara, Joanne Atkinson pointed out for me that Sugihara also seems to make some comments. Indeed, he makes some comments on the effects of noise. There's so much in his papers that it takes a lot of study, but he I think hints some at this impact, this interaction between, on the one hand, noise, and on the other hand, choice of dimension, particularly for an early paper published in the 90s where he introduced the simplex method for dimensionality assessment and so on. I think he may recognize some of these issues with high dimensions in the presence of noise. Okay, so this is a case without noise for an improperly high E, essentially minimal effect. Okay, we have slightly longer convergence time with high dimension. Now, if you're only dealing with the means, you can observe big changes in the values of means in the presence of noise. I find it more helpful to work with these plots. You notice improperly high E can cause slower convergence for a causal link in the presence of noise. So again, it's E and noise together operating, and we'll revisit when we focus more on noise. But note this slower convergence, E equals 32 at same scale, takes much longer to converge than with E equals 4, the true E. And you can get this kind of misperception. Okay, and without noise, they're pretty consistent. Right. So basically, with noise, you can be fooled by high E, by really big differences in E, like by a factor of 4, for example, but and more. And it can also, per Anahita's question, it can also change the asymptote. So you notice here, for example, an asymptote goes from the true E, but when we have noise and a much higher E, we can get a far higher asymptote, going from 0.075 to 0.3, factor of 4. Going from 0.00, so this is without noise, same change in E, basically no differences in asymptote. No noise, you basically get minimal difference in asymptote. By asymptote, I mean the sort of the high posterior density region, sort of it, where does it go to? Roughly the median. Here, with noise, improperly high E changes the asymptote, in this case, by factor 1.5 over 1.5 times. Without noise, same scenario, it's otherwise same scenario, same model, it's minimal. Okay. More cases. So with noise, if you have a non-causal connection, it can lead it to make it look causal with a huge difference in E, and the high density region is raised greatly in value. I don't fully understand why this occurs. As for many things, I suspect Sugihara may have some intuitions for this suggested in his papers, but I have not yet grokked it to that level that I see why this must be. I'm hoping someday perhaps to ask him. But it can change this posterior density and even make it look a bit causal. I think more experiments could also bear on that. Here we have a non-causal connection. This is the correct dimension. Doesn't look causal, but with an excessive E and noise, we get a big change in the location and the appearance of causality. So, ladies and gentlemen, is E important? Yes, E is important. Is E something where if we're off by a little bit, it's going to make a huge difference? Probably not. Probably not just a little bit. Probably you'll be pretty safe within a factor of 2. But the impact of E is vastly higher if you have noise. And if you have if you're way off in E and you're way off in noise, particularly if you have, it seems if you have a high E, like E, well into the dozens, into the 16 or higher, and you have noise, you can get fooled. Without noise or with low noise, I don't worry too much about it. This is actually quite high noise. These are my ground truth examples. Quite high noise here. It's really big noise. And here, by the time you get to 4 times the true value, E equals 16, you're starting to see yourself being in a region you could be fooled as to causality. This looks to me causal compared to this. Same thing with this guy. It's getting tempted to think it's causal. So E and noise interact in nasty ways. If there's high noise, you got to watch your E. You want to watch out for big errors in E. I'd say is one of my lessons. Okay, first order differencing. Some of you may recall this from my earlier slides, and I should probably call them up here just so that we can have them at our disposal. And you may remember that I introduced first order differencing, and I should really put those slides up here. It all went back. Great. You can tell what I'm going to be doing tonight. Okay, so ladies and gentlemen, you may recall that first order differencing. Here we go. First order differencing basically involves taking successive differences between elements of a time series. Before we do the delay embedding with it, with first order differencing, we'll transform a time series that looks like this into a time series where we take differences of successive elements. Why would we do that? Well, there are several reasons I've mentioned in my previous talk here. Whoa, no, that's not what I'm. Okay. One reason is that it can help reduce autocorrelation. It can help sort of detrend it, and it can help reduce spurious correlation. Sugihara makes a mention that he believes it can allow for better recognition of underlying dynamics of attractors. My own sort of take on it is that one should perform it selectively. So there's no questions that it can make a difference, for example, in means. So without first order differencing or with first order differencing, here without differencing, but with differencing here, it doesn't seem to make as big an impact. When do I perform first differencing? Well, I do have a rule, and this is based on my experience from now hundreds of cases. The rule is generally I perform first differencing when I'm dealing with a stock variable. By a stock, I mean a state variable that changes. It's an accumulation. It changes slowly over time. So it tends to be highly autocorrelated, right? If I'm looking at, for example, number of people with diabetes in year or 1, year 2, year 3, for example, that's a stock variable. Basically, the number this year will be very similar to the number last year with some flow, with some change to it that occurred. If I wanted to do it based on the number of people on an hourly basis in the acute care wards of our hospital, of RUH, say, then that would be a stock variable as well. It's a lot of variables that those in the audience will recognize as stocks. They change slowly over time by virtue of certain processes. There's other variables by contract that are not stocks. An example would be incident cases of an illness, number of suicides that have occurred for this given month. That's not a stock. It's not that the suicides for this month are the suicides for last month plus some delta. It's not like the suicides persist from month to month. There's no accumulation there. It's a flow variable. I perform first differencing when I cross map from a state variable, but not to a state variable. Okay, here's the idea. Do you remember in that last presentation that we were talking about, we talked about, for example, foxes and hares. Gosh, this is quite horrendous again. We talked about foxes and hares, right? Or lynxes and hares. And I argued, for example, that knowing if we know how the number of hares is dropping over time, it tells us quite a bit about how many lynx there are around, right? How many predators there are around. That's because what we're dealing here is the flow, the change in the number of hares. And in fact, if we think about when we characterize systems which involve stocks, we're dealing with the differentials of those stocks, or the flows of those stocks, or the focus of attention. The flows, ladies and gentlemen, or the derivatives are the things that are affected by other state variables. These state variables, y, don't directly affect x. It's not like x is a function directly of y. It's that x changes or y changes the derivative of x, or changes the flow into x. Same thing with classic compartmental models, right? Here, the number of new infections. So here, I is infecting S, not directly. It's not like I immediately change. It's I changes S is a function of I. It's I changes the rate of change of S. It's I changes the flow into and out of S. I changes the derivative of S. So when I think about asking to what degree does y impact x, or to what degree here does I impact s, what I actually think about is how does I impact the change in s, because s is a state variable. It's a stock. It operates. Things operate on it. Things change it. Things govern it through its flows. That's how state variables are changed. It's through their flows. The number of people in the hospital doesn't change every 3 seconds in some blinking way. It changes because people are discharged and people are taking in, at least any hospital I've been in. People are rolled in, people are rolled out, people, there's flows in, flows out. When we have stock variables, ladies and gentlemen, prevalences, number of people in a facility, numbers of animals, who are hares or foxes or what have you. These things change in a gradual way. They change through flows. And other things affect them through the flows. Other things affect them through their rates of change. Do you understand that? So the point here is, under those circumstances, I don't tend to ask, how does y impact x? I say, how does y impact delta x? How does it affect the rate of change of x? How does the number of foxes around affect the rate of change of the, the number of lynxes around affect the rate of change of the rabbit population? How does the number of susceptibles, a number of infectives around affect the rate of change of S? That's what I think about. And so I tend to do not x, if x is a stock variable, I don't do x map y. I tend to do delta x map y, because I'm interested in how it changes. After all, the value of x now and in the next data point may be very, very similar. So I first difference it, right? X today, this hour, the number of people in the acute care wards is 300. Tomorrow, or next hour, it's 301. Next hour, it's 303. It's not so much that other factors directly impact that value. It's that they change the rate of change of that value. So in short, here, when I do x cross map y, I do actually delta x cross map y. Okay, y could be a state variable or it could be a non-state variable. That's fine, but I don't delta it in either case, because it's I changes the rate of change of s. It's not delta I changes the rate of change of s. So here I do delta x cross map y if y is operating on x. These things are, so I is changing the rate of change of s. It's not the rate of change of I affects the rate of change of x typically so much as it is the direct variable. Okay. If we operate with undifferenced state variables, ladies and gentlemen, in my experience, it can cause problems. It can suppress the values of rho of the correlation, the Pearson correlation observed as we rise L, and it can also lead to, and I have this comment here, I don't remember the particulars of it, but can lead to spurious perception of sort of rising mean rho for lower L's, even in non-causal situations. Equally importantly, something Winchell has emphasized here is the fact that when we have state variables that are not first difference, there can be very high autocorrelation, which might require higher tau to avoid essentially pushing everything to the diagonal. If you're first differencing a time series like x, you don't need tau as large to sort of separate it on the diagonal. If x is a stock, the number of people in the acute care wards, and you look at it hour after hour after hour, the current values can be very similar to the last value. And if you use tau equal 1 and you embed it into three-dimensional vectors, and E equals 3 in a three-dimensional space, you're going to often have x of t minus tau, meaning t minus 1 here, and x of t minus 2 all being the same, and it's going to be on the diagonal. Whereas if you're dealing with the delta of x, you're going to be essentially detrending it or getting rid of a lot of that autocorrelation. So here's the results of, I have hundreds of these things. The results of doing these with raw variables with both first difference and the left-hand first difference here, ladies and gentlemen. So the left-hand side is the two are stocks, and if I have x map y, it's actually delta x map y. Okay. Here it's just the raw variables, x, x map, y. Here is delta x, x map, delta y. And you can see that it doesn't make a profound difference in these cases. When both are first difference, this is a little bit wider. It's not quite as tight. And there are cases where the raw variables can lead to some seemingly spurious components, and where this one as well. You notice this is without no. Oh, sorry, this is with noise. Okay. I think I'd have to go. No, this has got to be with noise. So here you'll notice if both first difference, you can get some sort of odd artifacts when you first difference both that you tend not to get with first difference only the left and not the right. This is with the raw variables. The raw variables can be a little bit wider in some cases as well. I used to think this was a huge issue. I'm not so convinced now, but I tend to hew to this principle based on understanding of how the governing factors work if I'm dealing with stock variables. So if I'm dealing with stocks and I'm doing A, X map B, if A is a stock, I will take its first difference. Sugihara in his work tends to, by my observation, he does first differencing a lot. I can't tell from his examples always if it's both are first difference or if it's this one. I'm not positive. But the jury's a little bit still out on this. I haven't found it. To be an incredibly profound thing, but it is something I take a little bit carefully. So this non-causal case, this is a non-causal case. If I just do it on the raw variables, this is what I get. If I do it with only the left variable, first difference, I get this, which indeed brings out the fact that it's non-causal. This is not causal. This looks, I mean, it's a non-causal variable. This looks to me slightly causal in the sense that the mean is coming up like that. Okay. And again, this is with both first difference. This is only the left-hand side first difference. I'm not sure why we get these artifacts, but these are even more wacko. And by the way, this is a causal variable. So this is with no noise. First differencing for both can lead to the upper fringe being suppressed. You'll notice here, this has an upper fringe here. You see it here. But when you first difference both, it tends to be less clear. And that upper fringe, to me, is a clear indication of statistical convergence. Or it points quite closely to the statistical convergence. When both things are cross-difference here, even though if we have an indirectly causal relationship here, it comes out with both the raw variables and the what I call flow difference variables, the left-hand side. But when you do first difference for both, you get this kind of impact that makes it look non-causal. It kind of turns it downwards. I'd have to go dig into why that is, but both first difference I see as not as helpful as left-hand side. So this is the one I prefer doing when the left-hand side is the stock. With the raw variables, I think you can do okay, but I think this left side first difference is a little bit better. So those are effects of first differencing. So we've gone through E, first differencing. Let's talk a little bit about tau. I think actually my earlier comments on tau are highly germane here. And I'll just go back in this other presentation to review them. Once again, a horrible calamity here. Okay. So the basic deal is, if your time series is such that it's very frequently sampled compared to the rates of dynamics, you're going to have a lot of repeats in your time series. And that is going to lead, when you go to examine it in an embedded way with tau equal 1, it's going to lead to things being on the diagonal. And you're going to need larger taus to spread them out. Because here they're on the diagonal, because the value at one time is basically the same as the value at the next, same as the value of next, and the value at time t minus tau, and time t minus 2 tau are basically the same. So they'll be on this point in the space where x, all three coordinates are equal. It's this diagonal along here. As tau grows larger, we'll spread it out. All right. And meanwhile, if you have a time series that's sampled sparsely, if you're only sampling occasionally within the time series, the underlying dynamic system, if lots is going on between the samplings, like you're only sampling the number of people in the acute care wards every 3 days, not every hour, but every 3 days, or you're only sampling the number of people getting sick with measles every month or something like that. In that case, I would say it's sampled sparsely. And if you use and there's no need to use a big tau to spread it out. Instead, you probably want to use a smaller tau because it's already occupying the space pretty well. You're going to have very different values for x of t minus tau, x of t minus 2 tau. So not everything will be on this diagonal. So you might want to use a small tau for that. Okay. So there are cases where changing tau, therefore, can lead to big differences. Generally, they're not huge in my experience, except where you have really, pronounced disparities, like you sample very frequently compared to what you want to, or you're using a large tau when you don't need to, potentially. So here's tau equals 1, here's tau equals 9. You could see this is a little bit, it looks non-causal, this looks causal. And I had some experiences that suggested there were some interactions with system noise that I still have to, in other words, the amount of noise in the system that I still have to explicate. There may be some findings on that coming up down the road. But if I were you with tau, what I would do would be to scan for different taus. I'd create a mean plot. I would examine your system with different taus. And I'd also look at the data and ask, how frequently is this sampled relative to the natural rate of change of the system? If it's sampled very, very frequently compared to the natural rate of change, you probably want to think about a larger tau. If it's sampled infrequently compared to the rate of change, you probably don't want to think about a big tau. Because if you do, it will lead to odd sort of twists in the dynamic, in the shape of the space and so on, by making it less continuous. Okay, I want to talk about effects of noise. Okay, here's a deep factoid. Ladies and gentlemen, we talk about the intrinsic dimensionality of a signal from different angles. One of the angles we can talk about it is by placing it in a very large dimensional space and assessing essentially how the number of points as we go out a certain distance within that within that space, a certain radius, how does the number of points rise? Okay. If what we're dealing with is a line, the number of points within that growing radius will go up linearly, essentially linearly, because we're just sampling a larger and larger region of a line. If we're dealing with a two-dimensional space whose intrinsic dimension is two-dimensional, as we go up, the radius goes up, the number of points caught within that sort of volume will go up with a square of the radius, because that's how two-dimensional things behave. You know, we have pi r squared, right? If we're doing with a three-dimensional space, and we increase the radius, if we're doing a three-dimensional structure, the number of points go up with a cube of the radius. And in general, we can use this technique. I think it's called the Hausdorff dimension, if I'm not mistaken. There's various dimensionality assessments, and I've forgotten which is which, but we can use that to assess the intrinsic dimensionality of a structure. But another way to view it, which harks back to some of Sugihara's earlier work, is to really talk about dimensionality of a trajectory as being how much information, how many past points do we need to predict the next point? Essentially, how much information do we need? How much state do we need to sort of make a prediction for how it will change in the next little bit? And turns out that if you need a large amount of information, it's a very high dimensional space. And that could be seen as needed to go consider the last n data points. Whereas if it's a very low dimensional system, it only has one element of state variables, maybe the current value is all you need to predict the next one. That's kind of the idea. But by that same perspective, that second perspective, we could say that noise, ideal noise, which we add to the system, has arbitrarily high dimension. No matter how many data points, we can't predict it. No matter how many dimensions we consider, ladies and gentlemen, we're not going to be able to sort of bound the number of dimensions associated with this sort of a trajectory generated by this noise. And what I'm saying here is that noise is a very high dimensional phenomenon. And it turns out that noise within our systems obscures causal and non-causal differences. CCM has its limits. And with a lot of noise, things that are in fact causal will appear non-causal and vice versa. And in the presence of noise, the asymptotic value of rho, of this correlation, this Pearson correlation, associated with a causal link, will typically go to a value less than 1. In the absence of noise, asymptotically it will go to 1. In the presence of noise, it will go to a value less than 1. Okay? And anecdotally, it seems to me that the larger the noise, the larger the deviation from 1, despite the presence of a causal linkage. As one adds noise in, the asymptotic level of a non-causal connection can also rise relative to a causal one. Okay, and it can make causal connections look somewhat non-causal and vice versa. The effects of noise can be amplified by changes in E. We talked about that earlier. And I say here tau, although, again, I think that needs further investigation. And analysis on higher dimensions, higher E, seems to amplify the effects of noise compared to lower dimensions. Noise may cause big disparities seen across tau. So take a look at this. I've shown you other graphs which show different cases where we have E in the successive columns. Here, I'm comparing the same basic cases. The top two are causal. The next one is indirectly causal and non-causal for no noise, medium noise, and high noise, ladies and gentlemen. And what do we see? Well, we see a lot of my comments borne out. With no noise, both the causal and the indirect causal pictures are pretty clear. We have this sort of odd artifact which remains to be investigated for X cross map W, but it does look broadly causal in terms of an early sort of upflow and then no subsequent decline. But even the indirect case is clearly causal, very clearly causal. The non-causal case, very clearly non-causal. In the top causal case, very clearly causal. With moderate noise, I call that moderate. It's actually quite high noise. I designed that case to really challenge it. But it's not, it's smaller yet than the very high noise in the far right side. So really this is high and extremely high, I think would be a better designation. With the sort of middle one, what we see is that we've lost the clarity about the indirect case. The indirect case looks arguably causal here. This one, the second one up from the bottom, looks only arguably causal. The non-causal case looks still clearly non-causal. This causal case looks causal. In fact, it looks oddly more causal than this. You've still got this little fringe down here, reminiscent of this beard. And here it also looks causal. With extremely high noise, this causal case still comes through pretty clearly. This one is being really challenged. This is extraordinary high noise. This is already very high. This is 5 times yet higher. The non-causal case still seems non-causal. This indirect one is pretty washed out. Okay. So this is another situation. This is with, I'm trying to figure out, oh, this is, yeah, these are other scenarios within that. So this is W, X map, Z. So these ones in the next slide are from the same series of scenarios. It's just they're different causal lengths. So this is a causal connection here. This is a weak causal connection. And you can see with medium noise, it gets challenged. It's kind of borderline causal. The fringe is kind of absent, but it's not clear that it really sweeps up. With high noise, it's just drowned out. This is a weak connection. It's a connection between sort of the two subsystems that's designed to be very weak to see the effects. Not causal looks not causal. Indirectly causal gets washed out even by medium and then blown away by high noise. Not causal here still looks not causal. This is indirectly causal. It's hopeless with extremely high noise, and even with high noise, it's pretty bad. Final couple cases. These are two very strong connections, causal connections. They stand through, even in the extreme noise case, they stand through very clearly. These are causal. This one's starting to get a little bit uncertain. High noise, they're still very strong. Not causal, looks not causal all the way through. So noise swamps things out, particularly for weak connections. And often a lot of indirect connections are weak because A's got to influence B, and then only some of that goes on to influence C. And so there's kind of a loss of transmission power along the way, as it were. But strong connections can still come through. You got to be careful. In my observation, a bigger problem for noise is that truly causal connections appear non-causal than vice versa. You can get, particularly if you're off an E at the same time, it can cause non-causal to look causal, but you have to be off, I think, an E and noise for that reason. These are all with correct dimension, E equals 4, but but different levels of noise. Take a look at a little bit more with noise. Okay, this is the interaction with E. We talked about it before. If you're off in both E and you have high noise, boom. This is with even, yeah, this is high noise, but and notice it changes the asymptote, right? And then this is without noise at all, no misperception, but here, you know, misperception. This is not a causal connection, but it appears causal. Not a causal connection without noise. Big E doesn't make a difference. With noise, you can fool yourself into thinking it's causal, and it raises this value. Without noise, little difference. With high noise, a weak connection gets drowned out. Without noise, convergence. This is not causal connection. W X map Z. I think this is okay. I'd have to look at this. This looks to me causal, and I'm pretty sure this is causal from the underlying system, but I'd have to check. Yeah. So W and Z. Give me a second here. W and Z here. W and Z. It is causal. Yeah, right here. There we go. So this is an error. This is in fact causal. Okay, and then there we are. Okay, yeah. With high noise, a weak connection. This is causal. It's not. It doesn't necessarily appear very clearly causal. And here this is causal. I don't know why this is labeled once again not causal. Okay. And adding noise can lead to quite big changes in asymptote for a causal link, and adding noise for a causal link can particularly bring it down. You'll notice this one, it's bringing down the value of rho from 1 to 0.65 to 0.17. As we're adding noise, it's bringing down the asymptotic value of rho. Similarly here, from 0.94 to 0.85 to 0.80, adding in noise brings down the asymptote for causal connections. These are pretty strong connections, or this one's strong. This one's decently strong. Adding noise for weakly causal link just washed it out. For a non-causal link, it still seems non-causal and non-causal there. Okay. Yeah, I'm not gonna go into this. This is okay. So how do I distinguish true cross-map convergence from statistical convergence? In my other lecture, I argued the basis of why we of how we can distinguish them, and why they differ. And sort of as we add points in, how a causal connection between y and x will yield different changes in rho than occur as you add points in for a non-causal connection, for a merely correlational linkage between y and x. But how do we tell this from the plots? How do we determine it from the plots? Well, I would try different e's and taus. I would make sure you scan for different taus, see if there's big differences. And I would try a couple different e's as long as they're not too large. And particularly pay attention to the region of L less than 250, okay? That's where a lot of action takes place. So here's another bunch of grouped examples of this. Ladies and gentlemen, no noise. You can learn to to recognize these things. No noise. This is no noise. This is non-causal connections. These are causal connections over here, the right. Causal, the left, non-causal. These ones indirectly causal. Okay? These ones all share a basic feature, a sort of rise up and approaching an asymptote without declining. Often it's rather lithe form as it rises up, and it sort of approaches an asymptote. This is something that needs to be investigated, but it still rises up there. By the way, you don't see this when you just do X cross map W. It's delta X cross map W. You see something even wilder when it's delta X cross map delta W. So I would actually try differencing and not try exploring several for those. These are indirect. You notice they show causal features. They show features in terms of their convergence. This is with high noise, ladies and gentlemen. High noise. So here we have non-causal. Here we have causal. Causal looks broadly similar with the exception of this weak case. This is the weak coupling between the two predator-prey subsystems. Very weak compared to the other connections. So, strong causal ones come through, weak causal ones become a little bit ambiguous. These are indirect. So here you have plenty of cases of statistical correlation are behind these. There's statistical correlation that's exhibited in their values here. But what we're not seeing is this sort of classic upward sweep components associated with causal linkages. And in my other slides, I also showed this. So here we, for example, have statistical dependence. We have some correlation in place, but you'll notice that this goes to 0.2 or so, 0.15. It's not going to 0, but it's very clearly non-causal, just from the shape of the envelope. Could I determine that purely based on the means? I wouldn't bet on it. I'd be afraid to operate on this without the means. I mean, with just means. It's really by looking at this envelope that I determine it. So this seems to me, from the envelope shape, to be quite clearly, it lacks anything convincing of causality. Now, you could say, what about these? These ones are clearly showing features of causality. Here they are indirectly causal, I happen to know, but they, with the exception of this one, which is arguable, the middle one, because it lacks a pronounced upper fringe, there's not a lot for me to suggest that these are causal. And, it's in the presence of high noise. Once again, it's a case of something that gets kind of washed out, these two being borderline, these two being washed out. So it's a limitation of CCM that it's not able to, resist the effects of noise for very weak connections. So, what should you look for? Look for this early region. Is it converging from below quite clearly, or at least not from above? If you see these sort of upper fringes where it's coming down here, these seem to me highly suggestive of correlational convergence, not causal convergence. At least they lack clear causal convergence. Okay, and from the mean alone, you might be fooled because you see a mean and maybe it dips down here a little bit. Look at the fringe, look at the envelope, it will tell you. Direct causality, direct causality, direct causality. sort of curiously direct causality. Again, I would look at X and W, not just delta X and W. This is X and W here. This is the raw values, and you see it's not subject to that. Although it does have this kind of lower fringe, it's not as drawn out. This is causal. This is indirect. This is indirect. Statistical convergence only, no causality. Only statistical. Right. This is with noise. Once again, no causality. You get these upper fringes. You get these upper fringes here. Upper fringes. And you could fool yourself from the mean plot. Take a look at this. Take a look at this. And this is the mean plot of it. You'd say, oh, well, it's coming up and sort of asymptoting. This is not causal, and it's quite clearly not causal by the fringe. Quite clearly not causal, but from the blue, you would think it's causal, or you could easily think it's convergent in a causal way. Upper fringe, no causality, but once again, you'd think it's from the mean alone. You might think it's causal. Okay. I think that is, so when we have, I guess I should say, when we have no coupling at all, here's some, statistical convergence. This is with noise, and I think this is no coupling at all between them. These are totally disconnected systems. No coupling at all between them. And you could still see there's a little bit of statistical convergence just as you need a large enough L to reliably indicate the row. Right. Okay. So I think that right. That is all of these comments I'm going to give today. This is a point of ongoing learning, but the picture is pretty clear. Basic picture being CCM tends to work quite well in my experience. It tends to give us a pretty reliable way, once we have a large enough L, to assess causality from one variable to another. It can assess, if we have X and Y, it can assess whether X influences Y, whether Y influences, so whether X influences Y alone, Y influences X alone, X influences Y and Y influences X. In other words, reciprocal causality, or neither influences one another. Pretty effective for doing that. I don't know of any other tool that can do that. It can do it based on empirical data because of how delayed embedding works and how in coupled nonlinear systems, a time series of just that piece of it, of one variable in the time series can tell us about the rest of the driving factors of the time series. CCM requires you to undertake it to specify a number of parameters. The primary parameters that you have to worry about are E and tau. But you also have to make decisions about whether you are conditioning the variables and how. For example, if you're first differencing them. My recommendations are, as far as first differencing is concerned, that you first difference when you are cross-mapping from a given variable to another. So you're cross-mapping from, say, X to Y. In other words, you're looking to see if Y is influencing X, the degree to which information about Y is encoded in the shadow manifold for X. In that case, I would, if X is a stock variable, if it's a variable that is an accumulation, and it changes via flows and through derivatives over time. so it has by implication very typically a lot of autocorrelation, et cetera. I would typically first difference it, but I would probably look at its non-first difference values as well, just to make sure you're not missing something. Remember that case with some artifacts. For tau, I would do scans based on at least means for different tau, but I would look more specifically at whether the time series you're looking at are densely sampled relative to the underlying dynamics or sparsely. If they're sparsely sampled, you probably don't want to use a big tau. You probably want to use tau equal 1. If they are very densely sampled, so you have value after value after value in your original time series that's the same, you probably will at least want to first difference it and maybe use tau that's larger, maybe. For E, I would run the simplex algorithm, which is provided in the REDM package, on your code. I would use it to assess its report of the dimensionality of your system, and I would try different E's around that, not automatically just using that. From some things that Sugihara has written, it would seem maybe we should use the highest value reported for prediction value from the simplex. I'm very hesitant to do that for something over 10. I tend to use, if it has a peak around, that's less than 10, and then it sort of declines, I tend to use something around that peak, but I examined several different values of E. Just my experiments have suggested, with ground truth, have suggested that E, within a range, it doesn't seem to have a huge impact. If you're way off, it does have a big impact, particularly, specifically in conjunction with noise. But for range, I'm not too worried about it. I'm hesitant to use any E over 10 because of the interaction with noise. And my experience is that high E's can lead to often can really change things that are not causal to look causal. So at the least, if you're going to do something with E over 10, I would do it for several different E's. Use per realization plots. Use them early, use them often. If you don't have the code for creating them, send me mail, send Christine mail, and we'll make sure you got the code to create them. Per realization plots are, to me, much, much, much more helpful than the sort of mean plots that we see in the context of most of the publications. So use per realization plots, and I would say with respect to the amount of data that you need, Sugihara et al., they give some examples which use dozens of data points, 60 data points, what have you. Something like that might be possible. I don't rule it out. I have not had that much luck with empirical data below a couple hundred. And even if we look at these cases, which I've been showing you, what you often find is statistical effects, like statistical convergent effects, like these upper fringes, are quite pronounced until about 250 or so, value of L 250. I particularly look at values of L below 250 to see what's going on there. If you see this upward sweep early on, sometimes it finishes early, and like here. But a lot of the action is in this earlier time. Try to sample densely from that. L's not every 10 for that, but every 1 or every 5 to sample from that. I'd be cautious about rushing to conclusions with data sets whose total length is less than 100. I think you have to explore them very carefully. So if I were to summarize in a few words, CCM is a technique that's not statistical, but based on theories of dynamic systems. It's a very powerful technique that, in my experience, works well, but it has its limitations, particularly in the context of noise. And in order to use it well, it requires some pretty intensive experimentation with a variety of values of E, tau, first differencing, and keeping sort of a pretty good record of your experiments. It's not without its flaws, but it's the only game in town that I know that operates like this. I think there's quite a bit of work still to be done to test it with certain types of systems, to test it in the presence of realistic amounts of stochastics, to test it in the context of interaction of noise and tau, and several other factors. This is the beginning of I think our learning as a group, but I hope I've communicating a lot of the most salient features about it here today. So that's all for today. I hope you found this the set of lectures useful, and that those online have done the same. And let's work together to try to advance the applicability of this technique going forward. Thank you. Thanks kindly.